yes, there exists a state of planetary emergency. That is not hyperbole, a state of planetary emergency. Planet Earth, we have a problem. I want you to think global, to treat the Earth as a whole in its relationship to its environment in space. So here goes. We know that increase in the concentrations of greenhouse gases raises the efficiency of the insulating envelope and reduces the net global radiation. If you look at those red little arrows pointing out that says the radiation we give out into space from the Earth just balances the radiation we receive from the sun, and that balance is what maintains the conditions for life. We reduce the amount of radiation going back. That means that temperatures start to rise at the surface, and that means provided there is just a single step increase in greenhouse gases, then slowly, as the temperature goes up, radiation goes out again, and we recover equilibrium. Sadly, it's not like that. We have accelerated the accumulation of greenhouse gases. It's not just a set step increase. It's going up exponentially. So the radiation levels are decreasing. So the heating is increasing. Oh, and by the way, feedback dynamics are also pushing the system even further out of balance and pushing us towards a hotter and hotter Earth response. Now that's the phenomenon we're going to look at in depth. So here we go. Problem, feedback dynamics, and the acceleration of climate change. Let's look at what actually makes climate change happen. Here we have increased carbon dioxide concentration drives the heat engine. You know, scientists call it radiative forcing. That doesn't translate into anything that most of us understand. They know what they're talking about. I know what we're talking about, but most people don't. Radiative forcing is global heating. It's the heat engine that drives the change. The temperature is the outcome of the heat engine. It's like you've got a big cauldron of water on your gas stove. You turn the gas up, that's the heat engine. The thermometer goes up slowly as a response. Right, this is the gas light. That's the thermometer. So, increased carbon dioxide drives the heat engine. So does methane concentration drive it. Other greenhouse gases drive it. There are effects from aircraft condensation to Earth, the contrails, to the aerosols, the particulates in the atmosphere. They affect the heat engine. So, of course, does the reflection from surfaces on the Earth, particularly snow and ice, savanna, desert, the difference between water and trees and mountains. And then finally, the cloud effects, which are so difficult to model. Light reflects from the top surface, but clouds tend to act as an extra blanket and keep you warmer as well. So they go both ways. And it depends on the height of the clouds, whether they're ice particles or water droplets and the thickness of them and the size of them. It's an immensely complicated modeling area. The energy that comes in from the sun is the driver, and there are some, obviously that's what helps the heat energy. There's a small amount of energy from what we call geothermal energy at the center of the Earth, which provides a little heating at the surface. But it's very small, and we can ignore it for the sake of today's work. Okay, so that's what drives climate change. Now we bring in the feedback processes. What we've done here is create a series of clusters of feedback. Each cluster is driven by one particular phenomenon, effect in the climate behavior, and has its own effect on a particular field of behavior. So, for instance, the cluster feedback group 1 is driven by increased concentration of carbon dioxide and affects the increase in carbon dioxide. All the rest are driven by temperature, a bit like this. So there we have the cluster F1 driven by and affecting on carbon dioxide. All the rest of the feedback processes are driven by rising temperature, and then they in turn act on the driving processes that turn the heat up, which puts the temperature up, which in turn drives the drivers, which puts the heat up, which puts the temperature up, which drives the drivers, which puts the heat up, which puts the temperature up, and we have a global feedback process. What they do? Now we could look at some of those in detail, and back behind this presentation is a 3-day seminar, so I'm going to be a little bit briefer than that this morning. But we could quite briefly look, for instance, at the methane cycle. And here we have methane that emerges from human activity, from plants and animals, bacteria, and methane released from store. That summed up gives the methane emissions, it increases methane concentration in the atmosphere. In the atmosphere, methane slowly breaks down into carbon dioxide and water vapor. Carbon dioxide adds to the CO2 stock, but the methane is a very powerful greenhouse gas and puts the heat engine up, it puts the temperature. Now there's a feedback cluster in the methane cycle which operates like this. It's driven by temperature, and the warmer the temperature gets, the greater bacterial activity and the increased methane production. This we already see. More methane production, more global heating, temperature goes up, bacteria love it even more methane, but you've got the idea. That's what feedback's all about. The next one, tundra permafrost, those great areas of the icy waste with fossil ice left over from the last ice age deep underground, and the surfaces which just thaw a little bit in the summer and freeze again in the winter. Today, they are thawing deeper and deeper and deeper. We have an area about the size of France and Germany combined in Siberia now engaged in quite rapid thawing. And in that permafrost are trapped deposits of methane and deposits of biological material which the bacteria then get out, and we get release of methane. More methane goes out, more heating, temperature goes up, more thawing, more methane, and so forth. And then the really big one, there is about 3 times the amount of hydrocarbon energy stored in methane clathrates, as they call them, the frozen lattices of methane stored in the shallow seas at appropriate temperature and pressure conditions. 3 times as much hydrocarbon energy in that methane store as in the total store of coal, oil, and gas combined. That's a lot of energy. As the seas start to warm with global warming, that methane can start to release. Last December, and in the months that have followed since, we know that the NASA satellite monitoring has shown plumes of methane coming up from the shallow seas off the north of Siberia as the clathrates in that continental shelf begin to move. Decades ahead. We have already activated the methane bomb, as they call it, but it's a slow burn. The oceans warm very slowly and mix down to the seabed, and then the methane comes up, and then the temperature slowly responds to that. So it's a slow but inexorable cascade feedback process. Gives you some idea. I'm not going to go through all the details of all the ones there, but it gives you some idea of the feedbacks and the mechanisms behind them. Oh, by the way, heating is applied to the whole Earth system, and it's vast. I mean, it takes time to bring a cauldron of water to the boil, doesn't it? Turn the heat up full, and the temperature goes very slowly up. Little bubbles form on the bottom. Now, the inertia of the world is vast. and the heat engine has to do this. So here we go. Heating from all sources drives the energy that slowly puts the temperature up. It has to heat ocean, it has to heat the land mass. It heats ice before it starts to melt. It heats the atmosphere. Melting of ice takes a lot of energy before the temperature changes at all. It's a phase change from solid to liquid. Oh, and evaporation of water, increased water vapor in the atmosphere, is also a phase change that takes a lot of energy. So the heat goes through those processes before it starts to make a difference to the temperature. And if we look at changes in temperature and base our strategic policies on observed effects of temperature rise, we have missed the point on global heating. What matters is what's happening to the heat engine, and strategic policies geared to observation of current effects are strategically disastrous in engaging with the system's behavior. Oh, and by the way, just to complete the picture, there's another feedback cluster hiding here. The hotter it gets, the less inert the system is, and the faster it gets hotter. That one's only been in the understanding of our science domain for the last few months. So there we are, and we can put in that final feedback cluster. Now that encapsulates the feedback and driver system of the global climate behavior. So, let's summarize. Most of the systems known to affect climate change are now in net positive feedback. Each feedback mechanism accelerates its own specific process. But as a whole, this complex adaptive feedback system consists of an interactive set of mutually reinforcing subsystems. Isn't that wonderful? What it means is this, that the output from one feedback changes the temperature a bit faster. That feeds into all the other feedbacks, so they reinforce each other. That's an unstable system. It can move very quickly indeed. The work of James Hansen from the Goddard Institute. Again, same sort of date from James' publication. The Earth's climate, remarkably sensitive to global forces. Positive feedbacks, accelerating feedbacks predominate. And that allows the whole planet to be whipsawed between states. It's what we call a metastable system. Small pushes lead to big movements. Recent greenhouse gas emissions place the Earth perilously close to dramatic climate change that could run out of our control. Great dangers for humans and other creatures and to the whole life support system of planet Earth. You see, we really do have a problem. So we're going to look at this issue of tipping points, and this takes us into the next station, beyond the tipping point. There have been 5 major extinction events in the geological history of the Earth, caused by massive volcanic eruptions or huge lava flow, or in 1 or 2 cases possibly, major asteroidal impact. We're now in the early stages of runaway climate change. There's no naturally occurring damping, braking system to stop it happening. It's our job. Strategically, we have to generate a negative feedback intervention of sufficient power to overcome the now active feedback processes. And by the way, in the time that it takes to make that happen, temperature goes on going up. And the temperature going up brings in more feedback. So our intervention has to be able to control and damp the temperature-driven feedback during the process of intervention. That is a very difficult task. Climate stabilization is the strategic imperative for tomorrow's world. And tomorrow starts now. Climate stabilization means reducing that heating to zero. Otherwise, the temperature goes on going up. Otherwise, the temperature goes on going up. How do we do it? Well, just like that. Just like that. We have to make an intervention that slows the rate of heating, stops it, brings it back down again. If we simply bring it down to the zero, to an equilibrium, we will have succeeded in stopping runaway change. We will have stabilized the planetary climate, but at a cost. Because the temperature increase at stabilization point will still lead to catastrophic impacts and tipping points and chaos in many of the climate systems. So we also have to go through some period of global cooling into negative radiative forcing, as they say, to make certain the temperature doesn't exceed tolerable limits. And then we come back to thermal equilibrium. That's the overall strategy. It is not, of course, the strategy being addressed through the IPCC processes, the Montreal protocols, and so forth. They are addressing a climate agenda that is way out of date. We often see our human institutions as supertankers, inert, dinosaur, rigid, difficult to change direction. But you know, human institutions are made of people. They're only inert because we project authority into the institution and give it power over us. What we have to do today is to deconstruct the dinosaurs and to move from the supertanker to the shoal. You know, shoals can respond very quickly. They can respond to threat, and they work together. The signals that go between the fish are almost instantaneous. In technical terms, it's the move from rigid systems of command and control to the flexibilities and resilience of complex systems of complexity, of multiple parallel processing, of distributed intelligence, of people power, of the emergence of social ability to respond to the crisis almost instantaneously and globally. We can do it. We have the support structures and communication strategies, mobilization for lifestyle change. This is not an impossibility. It is only impossibility if you cannot imagine it and then make it happen. So I offer you from supertanker to shoal as the transition in enabling solutions for tomorrow's world. Yes, there exists a state of planetary emergency. That is not hyperbole. There does exist a state of planetary emergency. Planet Earth, we have a problem. But Gene Kranz's philosophy in the response to Apollo 13 was not to bring in some Swedish economist to work out the cost-benefit analysis of bringing 3 men back to Earth. He said, no, whatever it costs, this is a question of survival. Failure is not an option. Thank you very much.